Alright, I'm going to explain to you guys how level shifters work and how to build a few different iterations. So what's the purpose of a level shifter? If you take an analog block that is sensing something, and in this case we're using this pot as a sensor, then that analog block has some sort of analog logic that needs to drive a digital block. And if this analog block has a voltage range that is wider swinging than your digital block can handle, and in this case we're saying that our digital block can only handle 1.8 volts to 0 volts. So we need to figure out a way of taking this output for the analog block and distribute it properly when we're feeding it to the digital block. So first of all, for experiment 1, you're characterizing just the analog block. So if you have an input of Vp, however Vp changes, Vout is going to respond like this for a comparator. And that's the hard switching that is explained in here. So it's just a step function. So you want to find values along this that shows this hard switching. So in particular close to this switching characteristic here. You can choose values out here as well if you want, but just make sure that you show the switching characteristic. Okay, so in order to get the V0, this experiment 2 is the same circuit. This part right here is identical. But now in order to go from V0, which is approximately, the rails are approximately 5 volts to approximately 0, we have to go down to V1, which we're assuming is going to be our digital block for experiment 2. Our digital block has to be 1.8 volts to 0 volts. So then this divider has to do this. It has to bring us down like that. So it's quite straightforward. This is just the divider equation getting us from V0 to V1. And the reason for all of these subscripts, we're saying that V1, the absolute highest that we're allowing V1 to be, V1 high max, is 1.8 volts. We don't want to, no matter what, we don't want to go over that. And when I say no matter what that means in this case, what we're doing is we're figuring out what happens if RB fluctuates due to temperature variations or whatever. Well, as RB fluctuates, it's obviously going to change V1 in some direction that may not be good for what we're trying to maximize at 1.8 volts. And the same with RA. So we need to characterize the variation in these guys, and we're assuming that we're allowing it to go up and down by 5%. So going from the first equation here just down to this guy, it's the same equation, it's just simplified so that we can look at the ratio instead of individual resistors. So this here is the ratio of those resistors. And as each resistor is allowed to reach its maximum variation of 5%, then this ratio is going to reach some maximal variation affecting V1 high max. So you can see that if this ratio RAB error, if this ratio is as small as it'll ever be, then that's going to contribute to V1 being as high as it'll ever be. So how do we make this ratio as small as it's ever going to be? Well, we look at RA and allow it to vary by 5%. That decreases the ratio, and at the same time allowing RB to increase by 5%. And these two combined are going to contribute to the minimal value that we should expect from the ratio. So this here is the variance that we're allowing. This here is the ideal values that we're designing around, assuming that we're going to get this variance. So plugging those values back into the same equation again, now isolating the ideal ratio and then the variation, what we want to do is we want to have this guy, the ideal values, solved for. We want to solve for that so that we know how to design ideally so that even if we have variation, we're not going to overshoot our max. And this V out high, that's the input to our divider, and that's what we're using there is what we already found in experiment 1. You're gonna find the VO max here. It's going to be one of these values here. So that part is pretty straightforward. Once you understand that all you're really doing is solving for this ratio, then you're free to choose RA and RB in order to make that ratio correct. And down here you'll just read this, that as long as you're within the neighborhood of no greater than 100K and no less than 10K. Actually, it should be around 100K, somewhere near those values. You don't want to be much more than 1 meg. Just, if you're over, once you get into the mega ohm, you're introducing noise. And if you're less than 10K, then you're losing power because you're allowing so much current. Okay, so you're going to build and verify that you're getting when the comparator is reaching its high, its positive rail, you're measuring that. When it's hitting the low rail, you're measuring that. And then verifying that you're within the range for your output of the divider. Of course, this should not exceed 1.8 volts. And this low should be somewhere near 0 to 0.5 volts or so. Okay, so for experiment 3 now, the only additional part is this circuit, which is, now it's a difference amplifier. So we're taking V1 onto the positive input, so it's going to see a positive gain. And then plus minus 5 volts here is on the negative side, so it's on the inverting side, which means it's going to see an inverting gain. And it's as simple as excuse me. It's as simple as taking what you've already done with this part. You've already done the divider up here. You know that it's just a comparator. Here, the output is just high or low, and then the divider is dividing that down to V1. So that's just a simple divider equation. So for that part, for the positive input, you're looking at this guy, because we have the output of the comparator, V0, goes to a divider, so this is what we've already done above in experiment 1. So we know that. Now take that, and for the positive, the component of the amplifier, the final stage, due to the positive input, is the gain on that times its input. Alright, so the input is V1. It gets a gain. So V2 here is V2 plus V2 minus. V2 plus is the component of the output due to V1, the portion that's on the positive, the non-inverting input, and V2 minus is the component due to that guy there. Okay. So essentially this entire lab is walking you through the derivation step by step. And now I'm walking you through verbally. So you see that the V2 plus is just the component of the final stage due to the non-inverting input. So you should know, or you should have memorized by now, I'm not going to derive it here, but the gain factor for that is just 1 plus the ratio of the resistors, this ratio here. The feedback over the S resistor, typically called the source, I think, anyway. So when it says to explain this, it's essentially asking, where does this term come from? It's just this 1 over. It more or less tells you the answer. We just want to make sure that you understand what's going on step by step. So this is the non-inverting gain term. That's all you have to explain. Okay, so now after substituting in V1 right here, which we had from above from the previous page, we end up with this. So that's pretty straightforward. It might look ugly with all the script R's and everything, but it's quite simple. I just noticed this has to be 5 volts here, not 15. Now for the other one, we have the output of the final stage due to the inverting input. And notice we have a plus or a minus here. We'll decide which one it is in a moment here. And the gain for the non-inverting side. And you should have this memorized as well. You've already taken an exam on it. So combine the two. We have the total output is the sum of the two. So here's the one term, here's the other term. And given that we have this equation here is written in 2 different ways, given that the comparator gives us a low and a high, we have to consider both cases. So, of course, the whole point here is that we want this to drive a digital logic still. So we're now at this point we're going from V0 of the comparator gives us somewhere around 5 volts. And in this now what we're doing is instead of being at 0, notice this is a critical key here. We're no longer at 0, we're now at -5 on the comparator, on the negative source. So the output V0, the output of the comparator, we're expecting something like positive 5 volts, something like negative 5 volts. And then we get our first stage divider, brings it down. Excuse me. But now since we're at 5 to negative 5, center is 0 is somewhere around here. Of course, we want it to be at 1.5 and 0, which means we have to bring this guy up to here, and this guy is going to go up or down wherever it has to go in order to be at 1.8 volts and 0 volts. And actually, I think what we've done here is 0.5 volts. So this here is V2, and this here is the intermediate stage V1 after the divider. So this gives us full flexibility to get from V0 over to V2, and we can go V2. We could have gone negative values or more positive or whatever. This is a full flexibility of this configuration. So what values do you actually use for these? Well, we already found this guy, the expected values from experiment 1. You should expect something like not 5 volts, but I would imagine something closer to 3.5 volts. So if you're expecting something like 3.5 volts for that, what about the negative 5 volts? Should you expect negative 3.5 volts? Well, it turns out if you look at the data sheet, which is what it's asking you to do here, for this guy, the data sheet will just come straight out and give you around 3.5 volts. And it calls this VOH, the high output. And then it'll give you the VO low output only for when VEE, which it's calling the low source, the negative source, is grounded. It only tells you when it's grounded. So what about when we have this at negative 5 volts? And by the way, in this case, it's going to say VCC is 5 volts unless otherwise noted. So it's actually quite simple for this part here, but for this part, it isn't as straightforward. So it's easy if you just use kind of a hand-wavy argument and say, well, when we have this condition, and it's always this condition, we're considering this condition always, but if it's this condition here, then it gives us VO low equals, I think it's like 5 to 20 millivolts. And you'll see if you look up this data sheet for this guy, and I suggest using the on semiconductor data sheet. On page 3, I think, you'll see a bunch of values, and on the far right of the table, it'll give you the units. And it's in millivolts for VO low, and it'll give you VO low when it's loaded down with either I think it's like a 2K. So it's suggesting that this output here has either a 2K load or a 10K load here. And we're using values that are at least 10K, so using the 10K load is going to be more accurate, more relevant to what we're doing. So if you're looking at what is it giving us for the 10K load, it's something like 5 typical to 20 max, I think. Then if we extrapolate that down to when this is negative 5 volts, when this is 0, when VE is 0, this is like 5 to 20. So when this is negative 5, we might expect VO low to be something like negative 4.95 to negative 4.8, something like this. That's 5 to 20 millivolts higher than the VEE. So I would write down here what you're expecting from the data sheet. Typical is negative 4.95. So using those two values, 3.5 volts for the high and negative 4.95 for the low, you come in here and you say, okay, you know the low, you know the high. You don't know if it's plus or minus yet. You know all of your resistors because you've already designed those previous to getting to these equations. All you have to do now is, actually, sorry, you don't know the resistor values. The whole point of this is now it's a new set of resistor values. The previous experiments were different resistor values, right? Because they're different conditions. So your variables are the resistor ratios. You have script R, Fs is one of your variables. Script R, AB is your other variable. And fundamental theorem of algebra, if you have two unknown values, which here's our two unknown values, then you require two conditions in order to determine those two unknown values uniquely. So these two equations are coupled, and it's also nonlinear because these are, in order to isolate these guys, these variables, that you'd have to have them multiplying each other. So you can't isolate the variables in a linear system. But it's a coupled because both variables show up in both equations. Two equations for two unknowns. And since it's nonlinear, you can't use a matrix solution. And I just suggest going to Mathematica's free online Wolfram Alpha tool. If you haven't figured out how to use that yet, just go in, and it's as simple as saying solve equation 1. So it has to be the entire equation with the equal sign. Equals, there has to be something equals something. So just put everything on one side and say it equals 0. Equation 2, put everything on one side, set it equal to 0. Or you can just leave V2s on one side and just write it exactly how it is right here. And these are going to be equations of two variables. Just call them x and y. And then just comma x, comma y. And if you plug this into Wolfram Alpha, it'll solve for both variables. And if you use the correct sign, let's say you start with plus. You have to use plus for both of these. It has to be consistent. So if you use plus to start with, then as long as both of these ratios are positive, then that's a valid solution. But if any of these ratios are negative, then that's implying that you have to have a negative resistance on one of those. So that's not a valid solution to this set of equations, which means you have to go with the negative and try that. And as long as you plugged in everything correctly, you'll get the correct answer for one of those, whether it's plus or minus. Okay, so that just by using Wolfram Alpha, or you can use MATLAB if you'd like. You can do this. You just look it up how to solve systems of equations. Then that's going to give you these resistors. Then build it and test. All right. So by the time I'm done talking, you should be done building and testing. Good luck.